Hey, Rob. I don't know what's wrong with my camera.
Yeah, you're a little hazy in the background there.
Yes, something wrong with it. It's the first time. It's not focusing. Let me just restart my computer and come back.
Okay.
Hey, Rob.
Hey,
I'm
good morning.
having camera problems, or?
Yeah, I was just gonna log on and log off and get back in.
Oh, no problem. How are you?
Doing fine. And you?
Good, good. I'm good. Good. Busy week, but good. I spent the week classifying things. Well, clustering things, but yeah. So very apropos to the reading. But, oh dear.
Yeah, I started to look at that paper again, and I agree, it's pretty interesting. And do you know whether the code is actually functional, executable that they provide?
It's older code, so it's based on Caffe. Basically, during the early days of the machine learning revolution, Caffe was the kind of back-end language of choice, and then everyone switched to TensorFlow, and then everyone switched to PyTorch. So you actually need older hardware to run the Caffe stuff, and it's a bit of a nightmare to configure because basically you're dealing with ancient code bases. So what we would need to do to use it would be to find a TensorFlow or a PyTorch version. I think that would allow us to run on modern hardware much more conveniently. But yeah, so definitely runnable. I've run Caffe in the past. It's just a very finicky thing to do. You can also just, if you have, does your academic institution have an agreement with Google or with Microsoft to gain access to cloud compute?
I think so.
So if you can get access to cloud compute, you should be fine, because basically they have a Docker container, which is a fully pre-configured environment set up, ready to go, and then you might be able to run a Caffe. Payam, have you seen a TensorFlow or a PyTorch version of the paper that we looked at?
I didn't look for it, but I would be really surprised if there isn't one, because that's a very highly cited paper. If you just search for the title and PyTorch or TensorFlow implementation,
yeah.
You should find.
I haven't done the search myself. I'm not asking you to do the search. I'm just curious if you already knew. But yes, I could research that as well. But yeah. So,
yeah, I bet there probably is an updated version around.
I would say so. I don't think there's anything particularly profound in the algorithm. It's more the theoretical thinking. So yeah. But very interesting.
Yeah, I haven't done a search on it, but there may be an updated version.
Yeah, I can do that while we're chatting now. Hi, Rose. Welcome.
Good morning, everyone.
Good morning.
Your little kid's okay? The one who was sick last week?
They're recovered, yes. Ran through the family.
I'm sorry?
I said it ran through the family.
Oh.
Yes, I remember those days.
Always fun.
We face different challenges as your kids get older, but yeah. Okay, so Payam, you had some questions. So Rose, last time we talked about this paper, did you have a chance to look at it at all, or should we give you a brief summary?
Paper, yeah.
Okay. Payam, why don't you ask the questions that you had for Rose, and then I don't paraphrase it. So
Yeah, I mean, last time we just talked in general about clustering algorithms, and different ways we could make it maybe more supervised all the way to completely unsupervised, where you just go cluster things. And there's of course lots of challenges because the clusters you get don't always correspond to what you want. So the algorithm usually just finds based on some measure of distance, which would be, I think the most naive one is the k-means clustering, where the distance is just a Euclidean distance between points. So the thing I guess it would be good to get your input on, like I thought this would be like I would be really surprised if people don't use clustering in medicine, in general in health, because I would imagine like some of the discussion we had before, like if you could show that two patients given their whatever features are short distance away from each other, in some sense that makes sense. That's what you want, right? To decide, okay, this drug is likely to work for them or not. So I wonder how people think about like clustering in medicine and health. Like I'm sure people are trying, but what are the challenges that you've seen?
So I know that people have had a lot of success with cancer treatment and like understanding different cancer types. And I think that's the place it's been most successful. I think there's been a bunch of stuff done with breast cancer cells where people have used clustering, and initially they looked at it and didn't really know what it meant, but by sort of following through, they were able to have some discoveries there that they wouldn't have had without clustering. And so I think that's probably where it's been most successful. I've seen people try to do it with EHR records, and I think it's really interesting, but it's also really, really hard. And so I've played with it a bunch with some of the stuff that I've done, and sometimes you get these results that like it's really compelling, right? You're looking at it and you're like, there has to be something here, but trying to figure out what it actually means, it's really hard, right? And you're just like, why did it come up with these clusters? Like, this looks really interesting, but I don't.
Yeah, could you give me an example?
Pardon me?
Yeah, an example of what you just mentioned.
Oh, so I mean, that I have done a bunch of research around thyroid treatment, and like a lot of the original research was done on a very different population than it's applied to. And so I had a large data set where I used clustering in it, and it got out these groups that were pretty distinct, but trying to understand what that actually meant in terms of who these people were and what the implications might be, it was really hard to like figure that out. I didn't ever get to the point where I'm like, oh, I understand what this means, right? When you're dealing with large dimensional data, how do you understand like what the cluster is telling you about this group of people? So I think that's what having a ton of domain knowledge. And I think if we also have some ability to understand what the components that make up the cluster are, like that's when I think you'll start to see. I mean, I think that's what they did with the cancer research stuff. Like they had a lot of domains looking at the specific cases, and oh, it's what this is. But the higher the dimensions are, the more difficult it is to do that. Does that answer your question, Rob?
Yeah, kind of. I mean, I've started to play around with the clustering too, and it's on one hand, I look at it and I think, oh yeah, this is really interesting, and then the other part of me steps back and says, wait a minute. So one of the things I did just kind of for fun is I generated a bunch of random data. And yeah, I mean, the clustering algorithms find patterns in that random data. And they're very strong. And you show them another data set and they're going to find the same patterns in the random data.
I mean, this comes back to a lot of the stuff we've been discussing, right? Are the things that we find, are they truly meaningful? Or do we just tell a story about them and find some way that we can manipulate them and then say we're doing something other than we are doing. I mean, it's hard, right?
Well, so what I was kind of thinking, is there a couple ways of approaching this? So in this finance problem I've been dealing with, I've got like 200 variables and they all kind of measure the same thing. And I was trying to see if there's sort of commonalities in the measurement. So this is stuff David and I have been playing with. So one of the things I did is I can do this on a daily basis. I can create these clusters on a daily basis. And then one of the things I did is I looked at whether there's sort of predictability over time in those clusters. So, you know, in some sense, if you've got kind of a stationary population that tends to cluster together, I mean, it's kind of nice that that has predictive power. So yesterday's cluster is going to help tell you what today's cluster is going to be. So, I mean, that's kind of, you know, I mean, I'm looking for intuitive measures of validation.
Mm-hmm. Yeah,
Another thing
way of identifying when we have data drift going on too, right? That's changing, like because of the interventions we've taken, that something different is starting to happen. Yeah, it's an interesting idea.
Another thing I did was I took the clusters and ran a cart model through it. I ran it through a cart model. So I asked, okay, so I've created these clusters, you know, out of these 200 variables. Now, what actually explains these clusters? And I mean, that was kind of interesting. You know, I got back results that kind of made sense.
So you were able to explain your clusters?
Yeah, more or less. I mean, but I'm still using the same, you know, 200 variables to explain the dimensionality reduction. So yeah, in some sense, you would expect it to work.
Did you
I mean,
try
that's the
PCA?
point,
And
right? You're always trying to get to an intervention, right? Or something you're
Well,
going
you know,
to do.
I'm not to the interventions yet.
No, but ultimately, that's what you're trying to do, right? Is get to the point where you can take some action based on what you've
Yeah. Okay. So I
and
mean,
get some different outcome for yourself or for some group.
yeah, just a second time. So here's sort of my thinking. And you know, tell me if this is nuts or not. But okay, suppose you're able to create clusters, and suppose in a cart model it says this particular variable matters for, you know, it's the most important one for distinguishing between these clusters. Now, can we think about that variable sort of now in an intervention sense?
Can you repeat that? Sorry, I missed it.
So could we think about tweaking that variable in an intervention? So if I change that variable, is that going to push this cluster from one to another?
So is it the is it a cause basically?
Mm-hmm.
Right. It's essentially everything else. Is it the initial object, the thing that everything else is derived from this quantity?
Yeah.
Or is
it
it
doesn't have to be a cause, right? It could just be correlation. I mean, you could
Just
push.
be correlation, yeah.
Which
But
is
if you
okay, right?
intervene upon it, then it has to be involved in the causal chain if you intervene upon it and it does something, right?
Yeah, all correlations have to be involved in the causal chain, I guess, right? Somehow. Everything is involved in the causal chain.
If it's correlated and it's just correlated because something else upstream, right? Like if you change it, it's not going to make any difference. But if it's truly causally involved and you're changing it and then it's impacting the outcome,
that's fair enough. Yeah, yeah.
Actually causally involved as opposed to correlated. That's actually a really cool idea, Rob, to then think, does it change the clustering in any way? Well, if your intervention is real, do you have some level of explainability here?
Yeah, and I'm still not sure about this this algorithm in this paper, how it's actually doing what it's doing. But to me, it sounds like it's trying to do something of the same.
Is it?
Did anybody run the algorithm?
No, I started the process of getting the old cafe implementation running on one of my machine learning boxes, but I didn't get to the end.
But before we do that, what we ought to do, or I can go ahead and do this too. I mean, when I'm looking at a problem like this, I'll go look at the original paper. And then I'll go into Google Scholar and see who cites the paper. And then I kind of start from the most recent and start working my way back. And, usually they come along with, every 3 months later, well, this is a great paper, but they didn't look at this area.
Well, there is 1,700 papers that I saw cited it, so enjoy. So here's a PyTorch implementation that has a lot of forks and stars, so this definitely works. Lots of people have used it.
Okay, great. Thank you.
So what does it
Have you
do?
guys played much with the different distance metrics?
I've studied them. I haven't done code on them, but I've thought a lot about them. But that doesn't mean much. I mean, nothing beyond the literature. So
I think that's the main point of clustering. Like if you don't pick the right distance, everything you get is junk. And the other one is the number of clusters is important, because if you pick the wrong number, again, you get junk. So it's like when you pick the number, is putting in a lot of assumptions. Sorry?
So why is that?
So like going back to your random example, you pick whatever 4 clusters, and he gave you 4 clusters because that's what you wanted and that's what you assumed you have, but you actually have 1 cluster of all random numbers. So you got junk because you picked the wrong number of clusters.
yeah, I've got a paper on this I've been reading. I'll share it with you.
Because I think in basically, like theoretically speaking, you have as many clusters as there are data points, right? Like in general, everything is unique in a sense, but you don't care about that. You want to somehow find some similarities, and you can tune that by increasing or decreasing your number of clusters from the number of samples to 1. And depending on how right you are, you might get something meaningful out of it. But I think you could totally get that wrong.
It's kind of like when we discretize stuff too, right? Like if you just split it based on percentages or something, it doesn't necessarily tell you that you really have true categories other than you've made groupings.
Yeah, but I guess the question kind of comes down to, are the groupings useful? I mean, it's not whether they're sort of right or wrong.
Yeah, so it's a completely, I think it's a domain question. Like the clustering algorithms knows nothing about it, right? Like if once you pick the distance and you pick the number of clusters, if you don't want to put labels on it, then I guess you just get the groupings you get, and then you see whether it's useful to you. And there's really no magic here. I think the magic comes in once you have some idea of what you want clustered together, and you get that, put that feedback into the algorithm, which is what this paper is trying to do. So then maybe you can guide it towards something that you care about.
I guess the number of clusters has always seemed to me like to be a little bit less of an issue too, that the distance is more important, because you could try it, right? Like you can easily try it and see how separate it ends up coming out and see if that seems like it's meaningful.
Yeah, there is a score they do, right? There's a score in the k-means that you just plot it, and you see beyond a certain number of clusters, you're not explaining any more variation anymore.
Right.
Usually there's like a kind of an elbow, and you pick the optimum number of clusters. But I think that ideally you would know how many clusters you're looking for from completely domain knowledge that has nothing to do with your algorithm. And I think that's the ideal case, but maybe that's too much to ask for.
I mean, I guess the thing is, what I like about clustering is that it forces us to give up some of the assumptions we have about what we know about it already, right? And so it gives us the opportunity to see it with sort of fresh eyes. Like, oh, I've never thought about it like this before, right? And so if we come in with too much domain knowledge of, oh, it has to be so many clusters, it almost destroys it from the beginning, right? Because
Yeah.
often what will happen is like low, medium, large, or right, like that we'll sort of think of, well, this is on the lower end of normal, this is normal, this is high, or at least that tends to happen in medicine a bit.
I have a actually interesting question. So I don't know if you guys, I used to work in fluid mechanics. If you remember, if you've done any sort of undergrad or whatever in your high school, like there's these concept of like non-dimensional parameters, right? Like you have the Reynolds number for a flow, which is like density times velocity times distance divided by viscosity. It has no dimension and it explains the regime you're in for a fluid. So if it's the Reynolds number is low, that means like a very low, slowly flowing flow. There's no turbulence. And as you go high, there's turbulence, and there's a whole bunch of like, engineers care about all these different regimes, and everything changes. But if you had a bunch of data, right? You had the densities, you had velocities and these, and you try to cluster on these, you get junk because they trade off of each other, and there's combinations that actually is exact same fluid. You just so knowing this Reynolds number or this non-dimensional like parameter really saves you a lot of time and requirement for data. So I wonder if you can do something like that. So Rob, I mentioned PCA. So you said you have 200 variables. Some of them, a lot of them explain the same things. If that's true, you would want to not keep all of them. I think you would want to do some kind of a PCA and see what subset of, what's the minimum number of the subset of the parameters that will capture all the variance in your data, and then throw away the rest and then do the clustering on that.
Yeah, that's certainly certainly an approach. How much is enough? I mean, what's your intuition?
No, you don't need intuition. The PCA gives you exactly how much of the variance.
No, it's a little more interesting than that. I mean, when I look at the number of eigenvalues that comes out of that, so the eigenvalue contains information, allows you to figure out essentially a proportion of the variance explained. So I think, yeah, the first one explains like 30%. If you go out to 4 of them, it explains maybe, I don't know, 70%. And then it's kind of a linear progression from there. So each new eigenvector explains, maybe 1% or something. So yeah, you could certainly do, basically create new variables that are the principal components and do the clustering on that. That's certainly an option. Yeah.
Yeah, I would even, maybe just based on what you said, I would even pick 3 so that I could visualize it and just look at it in the 3-dimensional space. If that explains already like 70% of your data or more, I think that's probably gives you some intuition as what those clusters would be.
Well, I mean,
they're weak clusters because they're only explaining 70%. I mean, that's a pretty big backdoor for.
Well, that was the first one,
phenomena.
right?
Hmm?
First variable was.
It's like 30% for the first one.
Okay.
Yeah, maybe 40. I can do.
I'm just saying that's a pretty big backdoor for,
Sure.
Yeah.
The challenge as I see it is, if we redefine the variables as the principal components, okay, so, I mean, I suppose it's true we can, once we have the clusters, we can work back and see what the actual data corresponding to that cluster is. Yeah, that's true. You could do it that way.
And of course, I mean, one shortcoming of PCA is that it's linear, which maybe in reality, most things aren't linear combinations of your variables, but I mean, it's a good start. I mean, there's non-linear PCA, but those are like harder to work with.
Doesn't that take away the ability to do what Rob was talking about, is identify the causality then? You're back to kind of correlation, right?
Well, I mean, if you did it in a PCA space, mean, you can still do a cart type analysis on your, well, okay, so now
You
your
can
underlying
do-
variables are principal components,
Right.
so it's going to be a little harder to kind of disentangle.
Yeah,
you
but we
know,
already know we can't get causality out of just data, right? So you have to have a model or have some bunch of assumptions. Like from your table of data, you have no causality. You could figure out what causes your clustering algorithm to switch clusters, but that has nothing to do with reality, I would say.
I don't know. I mean, suppose, see, this is kind of where I'm going with this stuff. Suppose we have the ability to identify which of these 200 variables basically causes you to switch from one cluster to another.
And Rob is talking about he's doing an intervention. So he's doing an experiment. See
Okay.
if the intervention, he's not
Right.
just using data.
But
I mean,
if it
That's-
works, so, suppose I think about, I don't know, going into the data, okay? So I built this model, and I've used this cart decomposition, and I said, okay, variable 17 is the one I got to tweak. So now let me go back in the data and take variable 17 and let me change it a little bit. And let's see what that does to, the future cluster that you wind up in.
Yeah, but I don't think that qualifies as an intervention. Intervention is in real world, not into your like tweaking your algorithm to get different results is not an intervention.
We're
You're
getting
taking the
close.
I mean, I think
seriously.
what you're talking about is the do calculus, right? This is Judea Pearl's do calculus.
Yeah, if you could do what you're
Oh.
proposing, you don't need to do calculus. Because you don't need a
And I
DAG,
think
you don't need
that's
to have a model.
Right?
Sorry?
That's the mechanism to do it.
Yeah, but that's
Yeah,
like a
it is
real
kind of,
intervention
yeah.
to generate new data, not to go tweak your input to see what your algorithm that just does something mathy that has nothing to do with reality actually produces, right? Because that you could always do, right? Even with a linear regression, you can go tweak your parameters and see when your classification or whatever changes, but that doesn't qualify as intervention, right?
Yeah, I mean, I guess I was thinking intervention in the real world. And see if it changes the clustering to give you some sense of causality.
So that's a different experiment because so there's a difference here. So Rob's doing rolling back in time, changing the parameter, and then reclustering to see how that variation in that parameter is driving other objects into categories. What you're saying is that we identify some principal component that we think has interventional power. We then do a trial in the real world to ascertain whether or not that factor actually does have a causal implication or not. So
yeah, that makes sense.
They're different.
Yep.
I'm not saying either is right or wrong.
Well, one works, one doesn't
distinction.
for causal analysis. Like
Right.
Yeah.
Yeah, I mean, you could potentially do, with this type of data, you could potentially do real world experiments.
Yeah, if you can do that, I mean, that would be amazing. Yeah, I assume the data set is fixed, that's what you have, and that's it.
Yeah, but it's, I don't know. I don't know anybody at BlackRock, but maybe one of my friends does, and we can call them and say, listen, here's, we want you to buy this, and we want you to sell this, and we want to observe what happens.
Must be some good friends.
Oh, dear. Interesting.
I mean, actually, I've seen that happen.
But why couldn't you do that quote unquote in vitro where you have a fake market without real money, but people like, don't they have simulated stock markets where people trade and try and?
That's also an idea. Yeah.
You have simulated stock markets?
Yeah,
Sorry.
Don't you do it to some degree too by identifying what, like you make a hypothesis, right? You say, oh, I think this is the piece that's causing it. And then you go out and you try and further subset your data and say, okay, well, these are the people where that condition holds true. Now I'm going to test my hypothesis against this group of people, and I would expect to see something different with this group of people. If you have large enough data sets, I think you can do some of it, at least by
Offline, yeah, you can do offline. I don't think, my understanding of causality is that you can't actually make any kind of causal inference offline. It has to be an online experiment where you actually test something in reality. Is my understanding. It could be wrong. I'm not defending my understanding, but my understanding is that that wouldn't work.
But
Unless,
assuming you don't have RCTs, right? I guess randomized control trials are kind of offline, right? You do it once, and because of the randomness, you could do it, right?
sure, no, okay.
I mean, I think that's the point with those data sets, right? Like with the DAGs, that you sort of form some hypothesis of, oh, I think this is how this works. And then you go back and you try and test that for particular subsets within it.
So you make a prediction while holding offline data that you claim has not influenced your prediction. You would then go to that offline data set, and because it's essentially opaque to you, it hasn't had a causal influence on your prediction. And so we could use offline data to make causal interventional inquiry. That's pretty interesting.
I think the prediction is coming from the person rather than like from domain knowledge, right? And then you're just using the random data set to try and either falsify or validate your prediction, your hypothesis. Sorry, let me turn that off.
Oh, that's fine. Interesting.
Yeah, I don't think keeping data offline and testing, that's basically what machine learning people do, right? They do validation. That has nothing to do with causality. You might still, because you can perfectly well use correlations to predict well, and your offline data, you might still do well.
But the point is that you make a hypothesis and then you test the hypothesis against your random data set. Right, there's some amount of human involvement or domain knowledge in terms of, oh, I think this might be what's happening. Right, so back to Rob's earlier thing about like the changing of clusters. So you think, oh, I think this is the element that when it changes, it causes whatever sequence of events to happen. So then you code that into a DAG and apply it to the random data set, and you can either falsify or validate. I mean, validate doesn't necessarily mean that's absolutely true, but you can falsify.
Right. So fast reject, sure. Yeah. So you're using the data as a means to do Popperian style. Well, it can't be this. So this is kind of abductio absurdum. It can't be this, therefore it has to be something else. What could it be? Well,
right.
Let's look elsewhere.
So to take an example, right? Let's say we have a huge medical record, set of medical records or something. I guess that's not randomized, but if you have some hypothesis based upon something you're doing in the lab, like, oh, I think this medication might work for this reason, and it's something that's out there already, you can then come in and try and see, like, if I group my patients in this particular way, did I see a significance when these people took this, right? It gives us some way of trying to get out of applying the same treatment to everyone all the time.
Sure. No.
So you have to have a hypothesis about your cluster, right? You cluster something, and then based on that, you're like, oh, I think this might be what's happening. And then go back and try and apply that to ideally a random data set. But I mean, even not random, I think you can probably.
So is a cluster a hypothesis? Like or is the algorithm that produces the cluster the hypothesis? Sorry, subtle point, but.
Well, I think when you start to think about it causally, the cluster is, right? Because once you've gotten to, like, the cluster is useless unless you think something about it, right? Oh, I think this is what this means. I mean, I guess it's useful for maybe for prediction. I don't know.
No, no,
Can I interject another perspective here?
yeah.
So when we talk about clusters, it's kind of a little bit of, I mean, there's a little bit of ambiguity involved in that. So the elements of a cluster, you're going to have, say, a centroid. Think of a k-means type version. You have a centroid, and you got some points that are close to that, and you got others that are much further away. In fact, at some point, if they get sufficiently far away, then they get pulled in by another cluster. So there's a distance measure of the strength of that cluster association. And, we're kind of, or at least in my mind, I have a tendency to sort of leave that out. But it does matter, because if you're trying to figure out how to nudge someone from one cluster to another, yeah, you probably ought to pay attention to that distance metric.
Yeah,
Maybe there's some that it just kind of takes a little nudge to move them, and others that, I mean, they're just kind of stuck in their ways. And so there's more to the clustering and sort of dynamics here. It's not just this, single classification.
Yeah, they do call that soft clustering, right? You have soft clustering versus hard
Yeah, I think that's
clustering,
correct.
where
Yeah.
so you do have access to that if you care about the actual how far away it is from the centroid. So I'm curious, Robert, how did you get to using clustering for your problem? Like taking a step back, if you want to predict something, why not just predict? Why do you want to cluster
Okay,
and
so
then explain?
Here's the problem that I've been thinking about. So, I mean, it's set up in finance, but I think it's actually much more general, lots of healthcare potential applications. But here it goes. So you want to execute a trade, a stock trade. Okay. So suppose it's a large trade. Now, your ability to get a good price for that large trade is going to depend upon, if you want to buy, I don't know, let's do another example. Suppose you're Elon Musk, and all of a sudden you decide you want to sell your Twitter shares. Okay, you got a big chunk of the company. Now, how can you do that? So if you just say, okay, I've got, I don't know, 10 million Twitter shares, whatever he has, and I'm just going to sell it on the market, what's going to happen is essentially the price is going to fall by a fair amount, I don't know, 3, 4, 5%, before enough people willing to take the opposite side of that trade step up. Okay, so that's going to be called a bad execution. Now, if he were to sell it in pieces, he'd probably get a better price. But there's a risk, and the risk is other people might think, oh, geez, there's more behind this order than just the piece I observed. Consequently, the price will kind of continue to waffle down over time. So this is a real world problem. If you're trying to do these trades, how do you balance out these two impacts? Well, part of it is you want to be able to gauge how much you could do at a point in time. What is the liquidity, quote unquote, of the market? So this kind of triggered the clustering. So we don't really know what liquidity is. We got these whole bunch of different measures. So the natural way to approach it was, well, are there clusters here? And are these clusters sort of associated with, like high, medium, and low? Okay, so can we observe those? Can we predict those? if so, then we could devise a mechanism that will allow us to do a better job trading if we know what, say, today's liquidity and tomorrow's liquidity is going to be.
But what is your ground truth though? It sounds like nobody knows what the actual liquidity number at any given point. So how do you know what your cluster or what you estimate is actually correct?
Well, yeah, I mean, I can look at real life, I can look at mean values corresponding to points in that cluster. So yeah, I mean, roughly speaking, it's sort of a high, medium, and low liquidity.
Mm-hmm. So can't you just like take all your data and classify into high, medium, and low classes?
Yeah, that's sort of what I've done.
Yeah, but you don't need clustering for that. That's a supervised algorithm, I guess.
Well, I mean, you could kind of turn it around and say, okay, now I've got the clusters. I'm going to use that as label data.
Yeah, I mean, yeah, but that's the point. I guess we can't really trust the clusters. Like I would trust the label that you would put on what the liquidity you think is at that given point more than what some random thing you get out of a
Well, for
cluster.
instance, there's stuff like, a bid-ask spread. So, in financial markets, sort of under the hood, there's always two prices you have to deal with. There's a price that you pay if you want to buy something that tends to be a high price. There's a price you receive if you sell something. That's called a bid price. The difference between those two is essentially the guys who provide the ability for you to do the transaction. That's kind of how they make their money.
Mm-hmm.
So they're going to buy at the low one, they're going to sell at the expensive one. They're going to earn the opposite side of that bid-ask spread. So, I mean, I can look at the data and say, okay, these bid-ask spreads are high in the low liquidity state, and they're, really narrow in the high liquidity state.
Yeah, my take on this was subtly different. I'll just share mine a little bit, was that at one end of the spectrum, so if you consider the spread being a sigmoid, at one end of the spectrum, you have one factor that essentially dominates, and that at one end, at the low end, it's what's called depth, which is the number of people willing to buy or sell shares at all. As the number of people who even care about this stock dwindles, the liquidity vanishes and it goes essentially at asymptotes to zero, to the point where nobody is interested in buying or selling it because it just there's no interest, right? Because
nobody's interested in buying or selling it.
Exactly. At the other end, you've got the transaction fees, exactly what Rob was saying, in which there's no point in trading because you're just giving money to the middleman and you're going to lose whichever way you go. So there are these two limits at either end of this sigmoid. And then there's this kind of, so if you think about the three clusters, you have one cluster at the bottom where there's no liquidity and nothing's happening. You have this other cluster at the top where transaction fees make it uneconomical for friction makes it essentially uneconomical to do any trades. And then you've got this third zone, this third cluster, which is actively liquid, which means that there's some depth, there's some level of latent demand and latent supply in the system. And there's enough new information about this stock that drives people to change their positions and drive movement in the stock market. So there's these three regimes which essentially you move between. So we consider those the clusters. And we're just trying to work out which, like if you're moving, I think that the interesting part is moving from the kind of the transaction fee problem to the middle problem, right? So if you're in a situation where you have a very valuable stock that's being very highly traded, then essentially that peters out and the transaction costs make it uneconomical to do that. So when something drops below that, when new information essentially pushes you out of this kind of cluster of transaction fees into the central zone, that's that intervention, that new piece of information arriving in the system that's moving stocks out of one state, one cluster into another, is what I believe Rob is hunting for. So, and also the reverse, which is something is moved into one of the other two regimes, in which case you want to basically just ignore it. So it all comes
so
down
here's
to
a
information.
question, like if somebody gives you a function that will map from like liquidity level to, I guess, how much it costs you to whatever, get rid of X% of your holdings, that's all you need, right? Like that's what you would want. So then it becomes a simple optimization problem that if given a time window of, let's say you have 1 week, you want to dump all your holdings, what is the best increments to do it in, given that you have this function that given a liquidity that you're going to cause by dumping large amount of your stock, you know what the price is going to be, and you want to optimize that sort of trajectory, right?
Yeah, that's the basic setup. The only challenge is, or one of the challenges, is you have to anticipate what those future values are going to be.
Yeah, so you need a function that will give you the future values given the current liquidity and how much you're going to try to sell.
Correct, yeah.
So that's the function you want to approximate. Okay.
Yeah, but getting back to sort of, Rose's perspective, you could think about these as being health states. You want to transition from one health state to another. Can you come up with health state clusters? Can you figure out how to drive the transition between those?
I think what's interesting about this discussion in the last couple of minutes is that when you know, so Payam, you're sort of talking about it as classification. And when you are classifying, you have some sense of what the classes mean. Whereas with the clustering, it's a discovery problem still. And you're identifying something that hopefully will lead you to some level of causality, right? So when you're doing a prediction around a classification, you're ready to make a decision, right? It's like fraud, no fraud, spam, not spam, right? There's an action you're going to take. Whereas I think the value with the clustering is that it's helping you to understand, are there different ways to think about this? Are there different interventions that you can take? And so, like, you could classify somebody in terms of fair health, good health, great health, right? And you want to move people between that. But it's really what causes fair health, right? Or what would cause you to move, right? Like it's getting to the point of identifying some intervention that you can take that will cause the move.
No, I think that's the perfect example. That's why, so that's exactly, I think that highlights my issue with it. So if you go, let's say you have some medical health data and you want to cluster people into good, healthy, unhealthy, and medium. If you go cluster it, like I would not trust those clusters. They don't mean anything. And you can't, by tweaking the parameters to switch someone from a bad health to good health gives you nothing. It teaches you about your algorithm.
That's because you're thinking about it in classes rather than clusters. The cluster is really about trying to build some new understanding. Is there something about what the machine learning has found that helps us to look at this in a different way? And can we form some hypothesis based upon that allows us to then come up with some new intervention that we can test?
Sure, yeah, that I accept. Yeah, I mean, if you just want to explore, get some intuition, and then go test it later, that makes sense. But just the clustering is not superior to classification because it's giving you nothing. It's like an ill-posed problem. It's equivalent to plotting your data in different ways and looking at it and see if there's any intuition you can get out of it.
Yeah, but if you can cluster on one data set and then form a hypothesis and then test that hypothesis in another data set, right? Or do an intervention to have a whole new set of interventions that changes the problem.
Sure, yeah, but how is that different than doing that the same thing with classification? let's say you already know
It's
if
the
there is some
discovery piece
people,
of it, right?
sorry,
It's the discovery piece of it.
but you're not discovering anything by clustering.
You
Maybe.
are, because you're trying to form a hypothesis about what the clusters mean.
Okay, so let's think of, sorry to get philosophical on you here. So the proposition that we're discussing here is the insight that we gain through algorithmic clustering an affordance to deeper understanding? Right. In other words, can by doing exactly what Payam says, which is looking at our data using different graphs to see if we can find some aesthetic in those graphs that leads us to an intuition that then leads us to an explanation. What the machine learning is doing is not coming up with the explanation. It's not even coming up with the intuition. It's just essentially trying to provide to you a new perspective on your data that you were previously unaware of. And so in that sense, it's not causal. What it's doing is acting as an affordance that essentially enables you to grasp something that previously you couldn't grasp. And I think that philosophically, that's a completely valid thing to do, right? It's the same thing as exploration.
I think that's fair. I think it goes back to what you said in the beginning. Like, it's all about that distance you pick. So once you pick that distance, all clustering is doing is visualizing it for you so you can have a look. Like, the clustering algorithm is not doing much, right? It's just sort of clumping things based on that distance. You can think of it as some kind of sort algorithm. I mean, yeah, I guess in that sense, if you know something about that distance, sure, the clustering helps you get more insights visually about your problem.
Right, so staring at the clouds might actually be a useful thing to do because they may form into a configuration that leads to an insight, that leads to an explanation that is a better explanation than
sure.
I think that's exactly the point, right? Is that sometimes when we come at a problem, we've sort of hard-coded a structure already for how to look at the problem. And by being able to give that up, we might see different structures. But once you go into it, looking at it, looking for a particular structure, and that's the problem with label data, right? You've already sort of decided what the structures are in one way or another.
You've already made a claim of invariance. Yes, you're saying that this thing is a cat, which it may or may not be.
Yes. Yeah.
Yeah, so I guess the spectrum of things, if you know it's a cat or not, it makes little sense to go to clustering to see how many different animals you have if you know. And if you don't know anything about your problem, I guess the only caution I'm giving is that if you pick a wrong distance, you're going to get garbage with beautiful clusters that mean absolutely nothing, right? So that's the flip side of the like assuming no structure.
So I think the point is to just try as many different algorithms as you can, and then you have to have some level of domain knowledge to be able to then look at what's come out and we're like, does this tell me anything? Can I form a new hypothesis based on this? I mean, it's not easy, right? But if you can, it can be very powerful.
Yeah, for sure. But then again, this is related to those discussions we had, like explanation and prediction, right? Like, what do you want to do? Like, what you're suggesting is great for science and explanation and devising models to do interventions. But if all you care about is prediction, you don't want to do any of that. You just want to do prediction.
Okay, I just wanted to try and bring up one subtle point here. I'm just going to share my screen for a moment. Just bear with me. Okay, you've seen this picture before, but so if I go one sec, sorry, carry on. 1 moment. All right. Okay, so let's do it this way and share my screen, and it's this one. Okay, so we have some grid of data, right? And we're sampling on that. And the distance metric is this kind of Cartesian XY metric, right? And I'm just trying to give you an intuition for the problem is that it's not an XY, right? There are other dimensions which are not linear. Right, so even though when we look at this from top down, we see it as 1, when we look at it in this dimension, it's not 1 at all, okay? So we are essentially the danger that we're in
Well,
is that
but let's slow down for a second. I mean, it's, yeah, you might call it Cartesian. I would call it, you know, Euclidean.
sure, Euclidean, sure, Euclidean,
Oh.
that's better, sure. Right, so we have this kind of Euclidean distance in 2 dimensions, which in this flat linear world,
But
it's
we
not
can easily
flat.
make it 3 dimensions.
But that's volumetric. That's not a manifold.
So hold on for a second. So each one of those kind of gray dots is a cluster. So in this representation, yeah, we've got 4 separate clusters for 2 variables, 2 dimensions.
Right.
Correct?
Yes.
Okay, so if we're looking at distance measures, you know, what's wrong with a Cartesian? I mean, so we really only have 2 dimensions here. Where does the third one?
It's a hidden variable.
Okay, so yeah, so hence I can't see it right. Okay.
Right.
Yeah, I think in this case, it seems to be like making the case that 2 dimensions is enough to tell these clusters apart, but you can probably move the gray areas so that in 2 dimensions they overlap, but once you go to 3 dimension, they're separate. I think
Okay,
that's probably
so
the point you want.
Right, in a third, so if we have a latent variable then.
So this to me is the kind of the clustering problem, which is if I have a latent variable where I can't measure it directly, right? It's this kind of hidden parameter. Can we use inference to essentially try and gain a measure of depth that takes us from this to this? I think that's what we're talking about intuitively. Maybe I'm wrong and I'm happy to be corrected, but that's my kind of underlying intuition, which is Payam's making a very valid point that if you only look at it in a Euclidean way, and we essentially ignore covariance or whatever you want to call it, some other hidden parameter that is varying and that is having an effect on the distance metric, then we're in this kind of inductive problem where we need the distance metric to infer the hidden variable, and we need a hidden variable to infer the distance, and it gets into this echo chamber problem. Anyway, I'm not sure if that helps, but
Also, what you're explaining, I think, is very related to what they call the kernel trick in SVM. So I don't know if you're aware of it.
why don't
So
you
that's
explain to us?
I just shared like a document that has a picture that might be, that's like if you look at just the top picture,
Right.
Is this,
similar to your picture.
Hold on a second.
Yeah, okay.
So that's like the basis
Yeah.
of how SVMs work, basically. So in this case, they want to classify things, and they are in 2D. If you look at it, it looks like all the points are sort of jumbled together. You can't draw a perfect line through it. So the whole kernel trick, which is a mathematical thing that they do for SVM, is it adds more dimensions, and then in the higher dimensional space, you can just separate the 2 classes with a line. So that's sort of the trick they do. So it's not exactly the same as what you're saying, but I think it's related.
Yeah, or if you go down in that post, look at the 2 concentric circle ones. That's even a better illustration of it.
Yeah, that's
Right.
a classic example they
Yeah.
use. Yeah, yeah.
Okay. I'm not trying to beat a drum here. I'm just trying to help drive intuition. That's all. I don't have a strong point to make, but essentially there's this cognitive trap where if something looks very familiar to us, we endow it with more significance than it actually has. There you go. I'll put it that way.
Yep, that's what I do.
It's a pretty good strategy, I think, for life. Most of the time until it fails.
Yeah, if it looks like a duck, talks like a duck.
Okay, so I just want to transition very briefly to some very, very interesting stuff I've been reading thanks to you, Payam. So I've been spending quite a bit of time listening to Kurt, what's his name? The guy. Anyway, so he came up with the free energy principle. Have any of you, I know Payam, you've come across it. Have any of you come across the free energy principle yet?
No. Although you mentioned it the other day, but
yeah.
try it again.
Well, I'd like to do this paper next time is my point. I'm just trying to see if we could jump into it.
Talking about Carl Friston?
Sorry, Carl Friston. Yeah, sorry, my bad.
Okay.
Yeah, Carl Friston. Yeah, so I've listened to like 9 hours of different podcasts with him, and very, very interesting guy. Anyway, he's come up with this concept of the free energy principle. I would highly recommend the 2 machine learning street talk. I'll post this in the thing if you like. There's 2 interviews with him on machine learning street talk, which are both very good. And he also has another 3-hour chat with the other guy, not Sam Charrington, but the other gentleman who does machine learning deep interviews.
Lex?
Not Lex. I think he's Theory of Everything, I think is the name of his podcast. Anyway, very, very interesting take on all of this. And he's come up with this very interesting idea called the free energy principle, which I think would resonate with us very strongly because it kind of counterpoints Occam's razor with necessary complexity kind of thing. So he has this very interesting measure, this metric of models, which is that they not only have to have predictive power, but they have to have robustness under uncertainty. And it's this, it's very interesting, elegant formulation. So he just published 2 papers. One of them is called Simple But Not Too Simple. And then there's another one which I haven't found yet, which I'll track down, which is even simpler. So basically he's trying to generate an intuition for this very interesting idea. So do we want to go deeper on clustering and just park this for a while? I think clustering is very interesting. I actually spent the last week clustering myself. What I'm trying to do is I'm trying to cluster units in buildings so that I can correctly identify which floor they're on, which sounds like a trivial problem until you actually try and implement it, in which case it's not trivial at all. So I think clustering is very interesting. I don't quite understand what clustering means, although I think we got a lot closer. So what is, I mean, there's lots of interesting questions here. Like, what is the difference between a classifier and clustering? And can we use a clustering algorithm to come up with classification metrics or classes? Like, is that a useful thing to do?
Yeah, you can do k-means classification. That's the thing. People used to do that.
They don't do it anymore.
Because it doesn't work as well as other things.
Okay. Well,
It works okay in simple data sets, but then when you get too complicated, it doesn't work anymore.
Okay. So what's your take? Would you like to transition to something a little bit more high level? I'm very happy to go deeper into clustering. I really am. So
I mean, I think the other stuff sounds pretty interesting. But I do have a general kind of clustering question. So has anybody seen, yeah, we talked about this, David, but has anybody seen prediction models that, I mean, if we went back to David's previous picture, so we've got 4 separate clusters. So is there a body of research that deals with estimating, you know, in a predictive sense, transition from one cluster to another?
Not that I'm aware of, but that doesn't mean it doesn't exist. It's just You know, the
Yeah, okay.
literatures are essentially infinite. So.
So I mean, it's you know, if we're looking at a logit model, it's a little easier. You know, we've got, so, you know, we're going from, you know, one state to another state. So that's pretty straightforward. You know, we can easily think of that in a cart type framework. But if you're going from one state to potentially multiple states, it's a little thornier. And this isn't kind of a standard Markov process because there may be, you know, the history may matter. So where you are is not necessarily a complete representation of you know, where you're going to go.
How you got here, right, basically. Fascinating questions, very, very interesting questions. So should we dig into that further? Rose, what's your take? Is this relevant to your work directly, or is it
I'm liking this idea of identifying how you move between clusters, because I think it ties into the causality stuff and then leading that into interventions. So I'd like to think a little bit more about this. I don't know that I have a lot to say about it now, but I do think it's an interesting question. And it takes us beyond, you know, we sort of have the idea of the SCM, but where we don't know if a latent variable is having an impact or not. I think tying this into causality, it helps us to how much do we need to know? And are we really manipulating the right things as opposed to manipulating things that are just correlations? So yeah, I'm interested in pursuing this.
okay? I think the free energy principle will help us do that. So I think we should briefly segue into the free energy principle to get that as a hammer in our toolkit. And then we'll bring that hammer back and see. So we'll return to clustering. No question, no argument. We will return to clustering, but I think we'll take a brief segue to the free energy principle. One other very interesting interview on the Machine Learning Street Talk, once again, thank you, Payam, wonderful resource, is a recent interview with Bengio. And he said something really interesting during that interview, which was kind of an offhand comment, which I think is actually very profound, which is modern deep learning is moving away from continuous higher order functions. They are completely going down the path of piecewise linear. All of the new models that are coming out, according to Bengio anyway, are trying very hard to essentially not use higher order, you know, multivariate manifolds and functions. And they're very much about local, smooth, Euclidean geometry, right? Linear models that are localized in space. So I think that that's a very interesting trend, and it's actually related, believe it or not, to the system 1, system 2 debate, where they're essentially trying to create very, very simple representations that are very compact that we can use to do higher order inference. And they just can't seem to get those to converge in anything beyond piecewise linear. So the current thinking, as I interpreted what he was saying, which is think locally. It's like think in a very local, local being a distance metric, which takes us back to classification. Oh, yes, yes. But if you think locally, and if you can create linear local models, then that's pretty much state of the art, according to what he was saying anyway. It's a very interesting insight. GFlow, do any of you use MCMC at all?
I've used it in the past.
So GFlow nets are a drop-in replacement for MCMC, and their fundamental purpose is to find sparse maxima. So essentially to try and increase exploration and to make exploration more beneficial and more efficient, so that when you are choosing a particular action, you may choose to switch from one local maxima to another and explore if that actually has benefits as opposed to just staying in the maxima that you're in. So it's very interesting what he's trying to do. we could also take a run at that at some point. So.
Hey, David, this paper you posted, when was it written? Do you know?
The paper, fairly recent.
Okay, I didn't see a date on it. So
I was just looking for contrasted material to the paper that Payam gave us, just to see what else was out there, basically. But I'm wide open to other papers in the clustering domain as well. So
next week we're saying we're doing this paper.
no, next week we're going to be doing, and I'll post it, and if you do, you
Okay.
follow
this
the.
one? I
Sorry,
think this one, right? Based on what you said, but maybe verify.
simpler. This is the. Yes, that's the one. Yes, so this is the paper we'll be doing next week. Thank you, Payam. Yes, if that's okay with everyone.
I mean,
yeah,
it's not a coincidence that he titled it this way, because I've seen many of his talks, and it's really hard to understand. That's why he keeps trying to make it simpler and simpler, because people just don't understand what he's saying.
Right.
So,
yeah. And if you don't have if you don't have a deep understanding of information from entropy from Boltzmann and from information theory, then it would be opaque to you. And it took me years to fully understand entropy from the Boltzmann / information theory perspective.
the guy who taught me econometrics, or his classes I took in grad school, went on to win a Nobel Prize, and for a good chunk of time I was pretty critical of him and how he approached his class and stuff like that. But you know, it eventually dawned on me that he was just fine as a teacher. I just wasn't a very good student.
Well, I wish my daughter would understand that, but yeah.
So I shared another book. I'm not suggesting we read it. It's like a 1,000-page book, but it just got released. And I think a lot of the stuff, I think, Rose, you bring up about making sequential decisions in a case where there's feedback. So this guy is basically trying to, I've listened to some of his lectures. So he's an emeritus professor from Princeton, and now he wrote this book. He's sort of bringing in all the different domains from like optimal control, machine learning, reinforcement learning, like other things, and trying to develop one framework for decision making under uncertainty when there is lots of variables. So that's his book is about like unifying the notation and bringing everything together. So I've ordered his book. I haven't received it, but he has like 4, I think, like 30-minute lectures on YouTube. Like if you just search his name, it'll pop up. And I think it's pretty useful if you actually want to like get into the nitty-gritty details of like sequential decision. I'm pretty sure like Rob, your problem maps to one of these approaches he gives in the, and he's a very pragmatic person. Like he's now he runs this company called Optimal Dynamics. So he has a lot of criticism for academia. Says, okay, this is great, but it's never going to work in any industrial setting or in a real world setting. And then he offers like, this is what he suggests you should do.
Yeah, I mean, I've got a fundamental question about this stuff. It's, you know, are we better off taking predictive models and using that as inputs into an optimization? Or are we better off looking at the loss function of the predictive models and building that into the initial estimation of them? I don't know the answer to that.
Can you say that in a different way? Sorry, I didn't fully.
Okay, so okay, so here's an example. You're looking at truck deliveries to a factory. Okay. Now, trucks can arrive on time, or they can arrive early, or they can arrive late.
Sure.
Now, the loss associated with them arriving early is not too much. They're basically just sitting around. The loss associated with them arriving late is large because they got to shut down the production operations.
Right.
Okay,
sure.
So if you wanted to come up with an estimation model, you could build in a loss function that says, okay, you know, for every minute they're late, there's a $1,000 loss.
I see.
For every minute they're early, there's a $5 loss. Okay, so you could build that loss function into your estimation.
Sure.
Now, if you do that, you're going to get a different estimate than if you do what we generally do, which is to have a symmetric loss function, you know, so whether you're early or late, you know, basically doesn't matter. So I don't know if you guys have thought about this, but it seems to me that there's sort of two alternatives. So one is to say, okay, I'm going to build this directly into the loss function, and that's going to determine my parameter estimates. Or alternatively, I'm just going to try and build the best predictive model of when they're going to arrive, and that's going to be an input into some other optimization model.
But don't you need a predictive model of when they're going to arrive, regardless of what's the cost of being late or early?
Well, but
I think it's inductive. I think that as we update, it's like a Bayesian process. So as we get new information, we update our priors, and that improves our ability. So I think that it's not one before the other. I think it's one before the other, and then the other before the one, and we just kind of.
But is it like, I feel like those are separate questions, like to predict whether when the trucks are going to arrive. So let's say you actually want to predict the time, and then your preference of them being early than being late, that's a separate thing that you impose on top of that prediction, right?
okay, so yeah, I'm not doing a good job of explaining this, but we're well over time, so I'll come back to that later. But yeah, lots of applications in healthcare too.
Very interesting. Okay, folks. Well,
treatments.
Should we call it there and reconvene next week?
Sounds
Payam, are you
good.
able to join us on Wednesday at all? Have you finished your?
Again, not. I have finished those meetings, but they keep putting in new things. I don't have any control over my calendar, so I would like to, but I might come in once in a while, but probably
Okay.
won't.
Well, you're
happen
always
this
welcome.
Wednesday.
That's how you rose. So
No,
yeah.
I appreciate it. No, please keep sending the invites. I'll try to make it whenever I can.
Okay. All right. I think we've lost Rose technically as well as otherwise. So see you guys
We
next
still
time.
see your
Okay.
smiling face, but anyway,
Thanks,
see you
guys.
guys.
All right.
See
Take
ya.
care.
Thanks,
Bye.
everybody.